All right, so for today's video lecture, we're going to be talking about particle collisions in one dimension. So collisions and impulse, this is in the impulse momentum section. One instance in which impulse momentum equations are particularly useful is when we have bodies colliding. So if a collision is between two bodies that occurs kind of quickly, we're going to have a system of particles and we're going to analyze them as a system as a whole with one impulse momentum equation for the whole set of bodies. We're going to have internal impulses between the bodies, but those are going to cancel each other out because the forces are always going to be equal and opposite, as well as the times are going to match up for those impact forces. And finally, external impulses are generally going to be negligible because of the very short time frame of the collision itself. They're going to at least be dwarfed by the magnitude of the internal forces from the collision itself. So all of this comes together in the conservation of momentum. So assuming we have no significant external impulses in the bodies that are colliding, we're going to have no change in momentum during the collision itself. So the impulse is going to be zero because the internal ones cancel each other out. The external ones are negligible. And so no change in the momentum of all the bodies final minus all the bodies initial. All right, so in this way, momentum is conserved. And imagine we've got two billiard balls, A and B here. So breaking down the momentum by body, body A and body B, and by pre and post collision status, final and initial, we're going to arrive at the following equation. So the momentum of particle A final plus the momentum of particle B final is going to be equal to the momentum of particle A initial plus the momentum of particle B initial. So if I know some of the final and some of the initial states, I can use this particular equation, and this is known as the conservation of momentum equation. And this one right here is just for a single dimension. So right now we're just worrying about a single dimension. We'll expand this into two dimensions later on. All right, so supplementing our conservation of momentum equation, the one conservation of momentum equation that we have, we'll be able to solve for a one unknown, but this usually isn't enough. So we're still going to need to get a second equation so we can solve for a second unknown. This is usually the final velocity of each particle. So if we know all the initial velocities, we'd have two unknown final velocities, and if we want to solve for both of those, we need two equations. All right, so the second equation we use is going to depend on the type of collision. So conservation of momentum is always our first equation. Regardless of collision type, depending on the type of collision, we're going to use a second equation that's going to fit in with our particular collision type. So the types of collisions, going from our kind of perfect bounce to no bounce scenario, most of them in the middle. We talked about this before with surface collisions, and it's going to be the same types of collisions here. So we're going to have elastic collisions. These are usually a good approximation of two rigid bodies colliding without any permanent deformation. 100% of that kinetic energy is going to be conserved, and so I can do kinetic energy final is going to be equal to kinetic energy initial. On the other end of things, we have inelastic collisions. This occurs when two bodies stick together after colliding. So if the two bodies come together, they impact one another and they stick together. The velocities of the two bodies are going to be the same after the collision because they are connected at this point. And this is the lowest amount of kinetic energy being conserved, though the bodies might still have some velocity in the end. And in the middle is semielastic collisions. So somewhere between elastic and inelastic, and the more kinetic energy is conserved than the inelastic collision, but less than the 100% I had for the elastic collision. And here we're going to have to use the coefficient of restitution. It's going to relate the kinetic energy before and after, or more likely, more directly, it's going to relate the velocities before and after. All right, so elastic collisions again. So when we have an elastic collision, we have the conservation of momentum. We can break this down to x, y, and z components later on if we need to. And for the second conservation of kinetic energy is going to be our second equation. So whatever, 1/2 mv squared is the kinetic energy of a single particle. So break that down into particle A, particle B before, particle A, particle B afterwards, sum all those up. We can't break this one down into components, though. Remember, kinetic energy does not have a direction in the same way that momentum does. So we can get three equations with this. For inelastic collisions, We again have two sets of equations. So first is the conservation of momentum. Same thing. Later on in 2D, we can break this down to x and y pieces. And the second equation states that the final velocities must be identical because the bodies are stuck together. So the final velocity of A up here is going to be the same as the final velocity of B. So that's our second equation in this whole setup. All right, so semi-elastic collisions is our last piece, and we're going to have two sets of equations, but now we're going to use the coefficient of restitution, which is a measure of the kinetic energy loss, or the kind of bounciness of the collision that we have. So conservation of momentum, that equation still applies. We can break it down to x, y, and z later on. And our second equation, we're going to use the definition of the coefficient of restitution for this. So this is going to be the equation when we have two particles at play. All right, so coefficient of restitution, we talked about this a little bit with surfaces. And for a simple body bouncing off a rigid surface, this was our value. So the coefficient of restitution, epsilon, is equal to negative v final over v initial. And when we have two bodies, so both of them have velocity, so it's not just bouncing off a surface. We've got one particle bouncing off another. It's going to be about the relative motion between those two bodies. So the v final, A with respect to B, and v initial, A with respect to B. So those relative pieces are going to be v final A minus v final B, and v initial A minus v initial B. So this is where our equation comes down here. This is a relative velocity piece. It's a relative velocity adaptation of this initial equation that we had with surfaces. All right, so this epsilon equals this piece here is our second equation for the semi-elastic collisions. And we would need to know what epsilon is in this case. And a little shortcut that we can use sometimes too is if we have an elastic collision, we can use epsilon is equal to 1 and just use this as well. And sometimes that's easier than doing the kinetic energy equation that we had earlier. All right, so bringing this all together, solving a collision problem when we've got two bodies like this, 3 steps. Again, number 1 is always set up your diagram. So you want to set up the diagram showing the initial state, set up another diagram showing the final state. So you've got two particles, each presumably is going to have a velocity beforehand. Each is presumably going to have a velocity in the final state. You want to identify what you know and what the unknown velocities are in each state. You want to identify the type of collision, so elastic, inelastic, or semi-elastic, and the coefficient of restitution if that's applicable. Next, you want to use the diagram to put together the conservation of momentum equation along with the other appropriate equation for the collision type. So the top equation here, this is our conservation of momentum. And we've either got conservation of energy, the same final velocity, or our coefficient of restitution equation is going to be our second equation depending on collision type. And so once we have our equations, we're going to solve for the unknown quantities. So we've got two equations. We can solve for up to 2 unknowns in this case. And with that, that's all I've got for today's video lecture. Thank you for watching, and I hope to see you again.